All right, guys, let's go ahead and tackle this Unit 2 review. Oh, look, this little calculator symbol means I got to use a graphing calculator for this. I think what I told you guys is that typically when you are on the calculator test, you should never have to take enter the derivative by hand, okay? There's always going to be a way for you not to do it. Now, this one isn't too bad. I could take derivatives here, but you shouldn't have to, right? Now, check it out. What's the least value of x at which the graph of f changes concavity? Well, what that means, okay? Well, a change in concavity happened at an inflection, and an inflection point is where the second derivative equals 0, okay, and it changes sign. All right. Now, I just learned this the other day, so you guys might want to practice this on your calculators and make sure it works, but it certainly seems to be working on mine. All right, so check this out. I'm going to go ahead on my graphing calculator right here. I'm going to go ahead and enter in this equation. So I've got cosine 2x plus ln 3x. All right, and then I learned the other day, this was new for me, right? That we can actually go and do a derivative with respect to x of y1. Okay, and we just put x equals x. And then I was thinking just now, like, well, certainly there's no way that I can take another derivative, but check this out, you guys. I actually think that we can. It appeared to be working for me anyway, so check this out. Now I'm going to take the derivative of y2 with respect to x. Okay? So, first derivative, second derivative, third derivative. That's so cool. Wait, I said that wrong. It's still cool though. Function, first derivative, second derivative. All right, isn't that super interesting? So interesting. We're only seeing it on the right side of the graph here because that's where ln of x is defined. Okay, so cool. Now look, just so I don't go crazy all over the place, what I'm going to do is I'm actually going to go ahead and turn off function. I'm going to turn off the first derivative, and I'm just going to look at the second derivative. So do you guys see this point right here? That is where the second derivative, the least point where it equals 0 and changes sign. So now all I got to do is calculate that 0. Okay, and I'm going to go left, right, enter. And that point is at 0.931. Okay, so that looks like that. Pretty awesome. All right, learned something new. I guess you can just keep taking derivatives over there. I don't know if there's a limit on that, but let's do it, you know? Okay. All right, this is going to be more of like a thinking question, right? Okay, so what does differentiable mean? Well, we know that if something's differentiable, it has to be continuous. So that's definitely true. All right. Now, does the limit have to exist? Well, let's see. If it has to be continuous, the definition of continuous is that the limit as I approach a from the left has to equal the limit as I approach a from the right, has to equal the point. That's the definition of continuous, you guys. This is the definition of the limit existing. The limit existing is kind of part of the definition of continuous. That has to be true. Does the limit as x approaches a of that exist? Okay, this, you know what that is? That is the definition of a derivative. Okay, there's two different ways to look at it. One, I don't know, let's just like kind of remember this, is the limit as h approaches 0, f of x plus h minus f of x over h. Okay, that's one definition of the derivative. The other one is the limit as x approaches a, f of x minus f of a over x minus a, which is exactly what that is. Okay, so if you remember those two, if something is differentiable, does that mean that the derivative exists? That's the exact definition of that, okay? So here's my last two things. Does it mean that f prime of a is defined? If it's differentiable, is the derivative of a defined? That's true. That's exactly what it means. So I feel like it means that maybe the second derivative isn't necessarily defined because we don't really know anything about that. So I think that's my only one that false. Okay. All right. Awesome. Let's take a look at this. Let f be a differentiable function. Okay, I feel like this is going to be important. F of 2 is 3 and f prime of 2 is negative 5. And g be the function defined by g of x is f times f of x. Which of the following is an equation of a tangent line to the graph where x is 2? Tangent line to the graph of g. Okay, you guys check this out. This is for the graph of, remember we go y minus y1 is mx minus x1. And we have some things we got to do here. This is my x value. That's easy because it's right here. All right. This is my y value. Since I'm looking at the graph of g, that's g of 2. Okay. This is my slope. And again, since you know slope is derivative, since I'm looking at the graph of g, that's g prime of 2. So we want to find a base. All right, this is a little bit weird because it kind of like switches lines over there, but g of x is f of x. That is a product rule. Okay, so here's my derivative. G prime of x would be the derivative of the first times the second plus the first times derivative of the second. Okay, now I got to go through here and fill in my points. I have y minus, I need to put y1 right here, equals m, x minus, x1 I already know is 2, so that's great. So I really just need to fill in the other things, okay? Now we said that the y value is g of 2. Let's find out what g of 2 is. It's 2 times f of 2. And up in the problem right here, it told me f of 2 is 3. So it's 2 times 3, so that's 6. Okay? Now I need to find g prime of 2 for my slope. G prime of 2 is 1 times f of 2, regular f of 2, plus 2 times f prime of 2. So 1 times, okay, f of 2 is 3, and 2 times f prime of 2 is negative 5. So that's 3 plus negative 10, so that's negative 7. There we go. Okay, that's got to be E. Oh, red. There we go. So y minus 6 is negative 7x minus 2. There we go. Okay. All right, cool, you guys. Let's see if we can work this one out. Definition of limit, definition of continuous, definition of differentiable. Let's remember what each of these are. Okay, the definition of a limit existing is that the limit as I approach some point from the left and the limit as I approach some point from the right are equal. That's where I have a limit. The two sides approaching are equal. Continuous means the limit as I approach A from the left, the limit as I approach A from the right, and the point are equal. F of A right here, this is the point. All right. Differentiable means it's continuous, but then I find the derivative and I make sure that for that, as I approach A from the left, and as I approach A from the right, that those meet up so that the slopes meet up too, okay? So we're going to check all of this. Now, one thing I want to notice is, all right here, it's equal to and it's less than. This represents the left-hand limit, less than 3. This also represents the point because it's equal. Right here, when it's greater than 3, that represents the right-hand limit, okay? So let's check if my limits are equal. All right, I'm going to plug in 3. 3 plus 2 is 5. I'm going to plug in 3. 12 minus 7 is 5. Does the limit exist? Yes. Is it differentiable? Well, does the point also equal it? Well, sure, because the point is up here, and so when I plug that in for the point, I also get 5. Okay? So now let's see if it's differentiable. So now I got to go, we take the derivative of that. So the derivative of these would be 1 if x is less than or equal to 3, and 4 if x is greater than. Now, if I plug this in, and like you guys see, there's really nothing to plug into, right? Because do the derivatives equal each other? No. So the following statements that are true are just 1 and 2 only, not different derivatives. They're not equal. Okay? Going to make a sharp corner. Basically, you guys, it's going to be a line with a slope of 1 transferring over to a line with a slope of 4. You guys going to have like a sharp corner right there. Continuous, the limits exist. Well, this looks fun. Okay, how many critical points does this have? Well, we need to know what a critical point is. Okay, definition. This is all this vocab that you guys got to keep on coming back to, yeah? On your flashcards. Critical points are basically just where the derivative is 0. So I got to take the derivative of this. Does this look pretty messy? But let's see how we can do this. Okay, this is a product rule. I'm going to go derivative of the first, and then it's a chain rule. It's just times 1, times the second, plus the first, times derivative of the second. Okay? Derivative of the first, second, and then first derivative of the second. That's also times 1 for chain rule. Now, we talked about this, I think, in class the other day, you guys. Here's the thing. If I'm trying to simplify this, because, like, what? I have to set that equal to 0 now. What we do a lot of times is we look for the GCF, okay? Now, check this out. X plus 2s, I have 4 of them there and 5 of them there. Does it make sense that I can take out 4 of them? All right? X minus 3s, I have 4 of them there and 3 of them there. So does it make sense that I can take out 3 of them? And here's what I have left. Okay, I took out all 4 of those, 3 of those. The left, I have a 5 and an X. Okay, here I took out 4 of those and all of those. The left, I have a 4 and an X. And what will happen is, this is going to become, okay, let's see here. Let me do this off to the side. 5x minus 15 plus 4x plus 8. So it's going to become 9x minus 7. That's my derivative. Where does that equal 0? Well, guys, I see 3 spots where it equals 0. When x is negative 2, where x is 3, and where x is 7 over 9. Now, here's the thing, okay? With critical points, it does not necessarily have to change signs. That's inflection points, okay? Inflection points have to change signs. Critical points do not necessarily have to change signs. So, here we go. Negative 2, 3, and 7/9. Oh, there are 3 inflection. Ooh, this is an interesting one, you guys. We have not talked about how to take derivatives of absolute value functions. So there's a couple different things I'm thinking here, because you really can't take the derivative of an absolute value. One thing I'm thinking, though, is what if we were to just graph it? Like, I know if I want to take an area for an absolute value, I definitely want to graph it. The other thing we could do is we could check both sides, right? We could check the derivative on left-hand side by doing, well, basically by switching the signs of that. And then we could check the derivative on the other side by leaving that positive, okay? Well, look, in this sense, this is negative x plus 5. So the derivative is 1. In this sense, this is positive x minus 1, and the derivative, I'm sorry, that derivative is negative 1, that derivative is positive 1. Derivatives on the both sides are not equal. I do not want this at all. Also, though, let's look at a picture of this, okay? Now, this is a no calculator problem, but, you know, this is kind of why we studied graphs, and, like, I want you guys to know what absolute value looks like, roots, you know, cubes, all this stuff, okay? All right. I'm going to rewrite this a little bit for you. What if I write it like this? And we did transformations. Does that tell you that we can go right 3 and up to, and basically just make our absolute value. Now this is asking what's the derivative at 3. And can you guys see that that's a sharp corner? So that's why that's non-existent. Okay. Number 7, pretty straightforward one. Actually, it's just checking to make sure you know this derivative. Now you guys remember that the derivative of e to the x is e to the x. The derivative of a to the x is a to the x times the ln of a. So 2 to the x is going to be x ln. That's just making sure you studied and you know your derivatives, okay? So 2 to the x ln 2, that's good. All right, let's see here. We got a couple of these free response questions. I've noticed over the last couple of things that we've done, you guys, some of you are forgetting implicit differentiation. So this is a really important one to go over. Okay, implicit differentiation. Check it out. I'm trying to take the derivative of that. I'm going to get 2x plus. Now, right here, you guys, that's a product rule. Remember, it's derivative of the first times the second, first times derivative of the second. And anytime I take the derivative of y, I use dy dx. Right here, this is 2y dy dx, because I took a derivative of y, and then equals 0. Okay? Now, do you guys remember the steps? I know we did this a while ago, but anything with a dy dx is like all this part right here. Right, here we go. Anything with a dy dx is going to stay on one side. Anything else is going to go to the other side. So I'm going to minus the 2x. I'm going to minus the y over there. And then I have x dy dx plus 2y dy. The next thing I'm going to do is I'm going to go ahead and factor out the dy dx's. Okay? We start it over again up here. Y dx. When I factor that out, I get x plus 2y is negative 2x minus y. And then when I divide that over, I get negative 2x minus y over x plus 2. And that's my dy dx. Okay? Write an expression for slope of the curve at any point. Perfect. All right. Question 9. Let f be the function given by function ln of x over x. X can only be bigger than 0. The derivative, oh, that's so nice. They gave me the derivative. I have to do it myself. Okay. The graph of the function has exactly one point of inflection. Find it. Okay, definition time. What's the point of inflection? Second derivative, 0, and changes sign. Okay, there's f. There's f prime. Time to get f double prime. Now I see why they gave me that. So I got to take the derivative of this. You guys, this is going to be a quotient rule, right? Quotient rule goes derivative of the top. Now, derivative of 1 is 0. Ooh, if negative ln of x is negative 1 over x. Derivative of the top times the bottom minus, okay, now I got to do the top times derivative of the bottom, which is 2x, over, oh, why did that happen? Hello, penguin. Just sometimes decides to drop off. I know it's not a penguin, okay, I was joking. A parrot. All right, all over the bottom squared, like, yikes, am I right? Okay, so let's simplify. X, cancel out. Okay, so that's negative x. For this, I think I'm going to just go ahead and move that up there. Minus 2x, 1 minus ln x, over x to the 4th. Now look, up here, I have two terms, okay? I have this term, and I have this term, and I have x to the 4th. And a lot of times what's going to happen on is you'll be able to cancel something out of all parts. On here, I cancel x from each of these, okay? So here's what I have. That becomes negative 1. At this point, I think I'll go ahead and distribute that. That's going to become negative 2 plus 2 ln x over x. There's my simplified second derivative. And you guys, when I'm looking for inflection points, okay? Oh, I guess I could simplify this a little more, right? Negative 1 and negative 2 is negative 3. Now I see why they gave me the first derivative, because that was enough of a pain, right? Now, here's the deal. When you're doing a second derivative and you have a fraction, like let's say you're making a sine line graph K, where the top equals 0, that's definitely a point on your sine line graph. Where the bottom equals 0, that could also be a point or an asymptote or something on your sine line graph. You got to take it into account though. So like 0 is going to be one of them. Now here's the thing though, it's only x is greater than 0. So my sine line graph technically will end right there, so that's why I can kind of ignore that one. Okay, let's look at the top part though. Negative 3 plus 2 ln x equals 0. Let's add the 3 over. 2 ln x equals 3. Let's divide by 2. Ln x equals 3 halves. Solve that. I have to do e to both sides, okay? So my final point right here is x equals e to the 3 halves. Okay, and that should be um my only inflection point, the x coordinate. Okay. You guys, number 10, we literally did this on review 1. So hooray! Just write something like did on unit review 1. All right, and we'll be back shortly with more.